This is part 9 in a series of videos in which I'm restoring and repairing a number of Intel MDS units. In the previous video I got as far as powering up the processor board, and it seemed to be coming back to life. I haven't refitted the DRAM yet, and in this video what I'm going to do is fit the DRAM, check to make sure it's operating the way that it should and that the DRAM has been accessed and that there are no apparent issues with the board. I believe this board works. I think some of the boards I have don't work, so we'll be able to use this by way of comparison and see how it functions before we start looking at the faulty boards. As I go through this series, I'll try to explain how the MDS system works. It is quite a complex system, and it's a bit unusual in its architecture, so I'll go through it bit by bit as I come to each part of the system. I'll describe briefly how it works. If you want any more information on a particular aspect of the system, then leave a comment and I'll post a separate video on that. But the first thing to understand with the MDS system is, although I've referred to this as the microprocessor board, it's actually just one of the microprocessors in the MDS system. There are in essence three major parts to an MDS system. Each one has its own microprocessor. So I currently have the logic analyzer clipped to the processor on this board, and this particular one is an Intel 8085. But there are, as I say, three major parts to the system. There's the main processor board, which is this unit. There's a in-out card which controls all the in-out operations, and it is quite a complex card. And there's a PIO card which really controls all the peripheral devices. And each of those three major components has got its own microprocessor. However, this board is responsible for overseeing what the system is doing. So this is really the arbiter of the system. It issues commands to the other two major parts of the system, and they are just there to do what they're told and respond to the commands that this particular unit sends. But it is also a multi-bus system, so on the backplane there is a multi-bus which we'll have a look at in the next video. And the way this operates is that any processor on the bus can become a master. And what that really means in the context of the MDS system is that any resources that are not strictly hidden by a particular module or particular card are available to other bus masters, so they don't need to be duplicated. So for example, if we take something like a floppy drive controller, then in theory any bus master on the MDS system can take control of it, and so the resources required to talk to and access the floppy drives don't need to be duplicated on each card. So it's quite difficult to explain, and I will go over it in more detail as we start looking at the details of the system. But just bear in mind that sometimes when we're looking at parts of the system, they may be being governed by another part of the system, and it's just the nature of the architecture that was introduced in the MDS units. But at the moment we're using this control card, the central processor card, standalone. It's not connected to anything else other than power and of course the logic analyzer. And so what we're going to do is see if it is functional in its own right. Now in theory, for this to run to a minimal degree, it does not need the other two modules attached. That's the other two main modules, the in-out and the PIO. It should run, and it should be able to access and run the ROM code without the other units plugged in. We won't see anything on the monitor, of course, because the monitor is controlled through the in-out card, but we will at least be able to monitor the signals on this card and see if it's doing what we expect it to. I won't go into too much detail on camera with this. I'm going to do quite a lot of checking, but it would get quite tedious for me to go through all the different aspects. There are a number of components on here that are specific to this particular card, and they're not made available to the outside world and to the other bus masters. So I'll test those in isolation. But what I want to do in this particular video is to refit the DRAM and make sure that the card is operating within its own sphere, its own world, and once we've established that is working, we can start connecting the other devices and see if they will interact in the way that they should. And along the way I'll add more connections to the logic analyzer, and we can interrogate the system and see how it's performing and how the various parts work. So the first step before I start to refit the DRAM is to make sure that the microprocessor seems to be operating in a sensible fashion. As I mentioned in the previous video, it's an 8085 and is a bit of an odd processor in that it doesn't have a separate data bus. The data bus, which is 8-bit data bus, it's an 8-bit device. The 8-bit data bus is shared with the lower 8 bits of the address bus. But some interesting points on this processor are that these 3 pins here, RST, they're actually the internal phase, if you like, of the machine cycle. So we can actually look at individual machine cycle state with this particular processor, which makes it very interesting to look at on a logic analyzer, because you can almost look at it on a machine cycle by machine cycle view rather than just instruction cycle. We'll come back to that another time, but just bear that in mind that it's a bit of an unusual processor, but it is quite interesting, so it should make some quite interesting videos. But the first thing I want to do is make sure that this is running at all, in any way sensible. So what I'm going to do is look at the ALE line and see what that's doing. So I'll just retrieve this probe. The board is of course switched off, and then I'll connect this to the line that we're interested in. Okay, and I'll now power up the board, and we should see some activity on that line if the processor is actually running, which it is. I should be able to halt the processor by holding in this key. It refreshes some latches, and effectively it creates a reset, and it should stop the processor from running, which it does. So that's a good sign. It means that the processor does at least seem to be under the control of the board, and it doesn't prove that it's running, of course. It doesn't prove it can access ROM or RAM or anything else, but it does prove that it's able to start up on its own, and it's actually carrying out sensible cycles on the card. What I'll do now is hook up to one of the data lines and make sure that what we're seeing on the data bus also makes sense. As I mentioned, because they're shared with the lower 8 bits of the address bus, is quite a good indication that the system is running to a fairly reasonable standard. Okay, so I'm hooked up to a data line, or data address line. We'll power the board back up, and again we can see that we are getting what looks like good data. It won't be the correct data, of course, because we don't have any RAM fitted, but again we should be able to stop the processor, and it should restart when I release the key, which it does, which is a good sign. Next thing is I want to start refitting the DRAM. Okay, so before we start refitting the DRAM, I just want to carry out a few basic checks. We'll see if the processor is actually trying to read and write the memory. This memory is specific to the processor card, it's not part of the bus master system. But what we should see is that the processor is trying to write data to the DRAM, and it's also trying to read data from the DRAM. Because the system's not running, then that is of course going to be fairly odd reads and writes. It's not going to be proper system read and write because the code isn't really running properly. But it's an 8-bit system, so there are 8 1-bit DRAMs per bank, and there are 4 banks. So what we can do is just populate one bank at a time and test it. So if we look at the data in pin, we can see we are getting some activity on that pin, and it looks reasonable. We don't really know what it should be at this point. And if we look at the data out pin, it shouldn't be doing anything at all. It should be floating because there isn't a DRAM there. So this should be the input to the buffer. And of course, there's nothing there. If I restart or reset the system, then we can see there's nothing on that line at all. What I'll do now is fit just one DRAM, and I'll then test the voltages, make sure they're still correct. As I mentioned in the previous video, these are 3 supply devices. I'll do that off camera, and then I'll get the camera back on and we'll see if we're getting any sensible activity on the inputs and outputs of that DRAM. Okay, so I've got one DRAM plugged in. We know all the DRAM work. I tested those as we saw in the previous video. We'll turn the board back on, and now what we'll do is we'll look back at the input pin. That looks fine, and we'll look at the output pin. Okay, now it's still floating, but then that's kind of what we'd expect to see at this point, because unless the DRAM is actually being actively accessed by the system, then the output's going to be tri-stated. What we should be able to do is force it to be accessed by the processor. So if I reset the system and then let it out of reset, we can see that there's activity on that line, and that's because one of the things that the startup sequence does on the machine is to clear all the DRAM, clear memory, and so that means that when it first boots up, we will see some brief access to the memory if it's working as it should do. Okay, so I'll now fit the rest of this bank, and I'll then do the same test across all 8 devices. Okay, I've fitted the entire bank of DRAM. I'll now power the board back up, reset it, and we should now see some activity on the output of the DRAM. It should now be running because we've got the entire bank in, and because I fitted this particular bank, we should see some activity on the system. So whereas before it would only access the DRAM briefly when we did a reset, it should now be continuously trying to read to and write from the DRAM. So we'll check each one in turn. Okay, that's looking very promising, and also the minus supply is still only showing 1 milliamps, so these aren't drawing excessive current, and the signals on the outputs of the DRAM look quite reasonable. Okay, so what I'll do now is fit the next bank of DRAM and we'll test those. Okay, so I've got the first 2 banks of DRAM fitted. I'll now power up the board and we'll test to see if those 2 banks of DRAMs are working. So again, what I should be able to do, if it's not being addressed, I can perform a reset and we should see the activity as the memory is cleared. Okay, it's looking good. I'll do the same thing now with the remaining 2 banks, and then once I've got all 4 banks fitted, I'll get back on camera and we can look at the next test. Okay, so I've got all banks of the DRAM refitted. We'll do a quick test to make sure that all 4 banks are working. So what we should be seeing, as I say, is the memory being cleared when we recycle the system. And that's looking fine. I'll test all these individually off camera. So what I'll do now is I'll check the memory refresh to make sure that the memory banks are all being refreshed the way they should. But if we now look at the RAS signal, that's the row address strobe signal on the DRAM, that should be being toggled every few microseconds as part of the DRAM refresh cycle. So we'll look at that pin 4, we'll look at that, and as we can see, that bank is fine. and the next one should be doing the same. Okay, that looks fine. We should see some slightly different behaviour again if we do a reset, which we do. Okay, so that's looking very promising. I'll connect the scope back to the data line, and you can see the data does now look very different than how it appeared before. I'll again halt the processor and we'll let it restart. And a couple of things we can see is, firstly, the activity at the beginning is not the same as what it ultimately settles down to, and that's a good sign. It means it's actually doing something rather than just continually running around in a tight loop. So I'll try one more time. Okay, that looks good. So the last thing I'll do in this video is we'll have another quick look at the logic analyzer and see if we're getting more activity on the data bus than we were last time. So the analyzer is set up exactly as it was before. All I've done is reload the same configuration. We should now see some activity. I don't know what it will be. It will just be something as part of the normal startup of the machine. We'll look into the exact details of the code another time, but I'll now arm the analyzer, and as we can see, we have indeed captured something specific. Also note that the lower 8 bits of the address bus, which is the blue trace, are the same as the green trace, which is the data bus, and that will always be true, of course, because even when the processor is outputting or inputting data, it will be the same 8 pins. And what we can do is scroll across and start tracing through the code and see what it's doing if we want to, but as you can see, it is now at least doing something, and so we can now start doing some more thorough investigation of the board. So that's what we'll do in the next video. We'll have another look at this board, a bit more detail on it, what it does, how it operates. I won't go into too much detail because I'm sure that I get a bit too boring, but as we go through the rest of the system and start to reassemble the entire MDS unit, then we'll start looking at the code and how the entire unit functions and how the various bits interact. So what I will do initially is assemble one of the units fairly quickly and get it up and running, and then we'll backtrack a little and start looking at the various bits in more detail, especially when we start looking at the faulty units and then we start doing some fault finding.